Hello, I'm Seema and welcome to part 14 of the chapter Redox Reactions. In this video and the consecutive few videos, I'll be telling you about redox reactions as the basis of titration. If you look at this topic in your textbook, it appears to be a topic of just one sheet and you feel it's not very significant, it's not that important. While actually titrations and the very method of titration is extremely important in chemistry, and not only is titration important to you in class 11, it will be very important to you in class 12 also. And redox titrations especially are not included in class 11, they are included in class 12 and therefore are very important for your board exams too. So I'll take it slow. What are titrations and what is the basis of titration? Titration is a technique that we use to find out the strength of a solution. When you say what is the strength is represented in terms of molarity, normality, molality. That tells you about the strength of that gives you an idea about the strength of a solution. That is, how concentrated or how dilute is it. So if you have an unknown solution and you have a known solution, if you know the stoichiometric equation between those two components, you can find out the concentration of the unknown solution by making it react with taking samples of both and making them react with each other, and with the help of an indicator you come to know it gives you an indication that the reaction is complete and you come to know what is the concentration of the unknown solution. You have been doing acid-base titrations in class 11, and if you have not done it, you will be doing it very soon. What is the basis of acid-base titration? What do you do in it? I'm not going to discuss the apparatus here. I'll be taking up video lessons separately for each titration that is there in your syllabus. Right now, we'll just understand theoretically what happens. When you take an acid and a base, when an acid reacts with a base, neutralization reaction occurs. You studied this in class 10. So when neutralization occurs, for example, you have HCl, I'm just using this base to write it. You have HCl combining with NaOH. It gives you NaCl plus H2O. Now, NaCl is a salt and water is neutral. HCl is a strong acid, sodium hydroxide is a strong base. So an acid reacts with a base to give you a salt and water. So the acid is neutralized and the base is also neutralized. Therefore, these reactions are known as neutralization reactions. Now, how can you identify, if you, let us say you have one of these whose concentration is known to you. Let us say you know the concentration of the base or you know the concentration of the acid. You take a measured quantity of you usually take the base in the burette. You would be doing these titrations in 11th, and if you've not still done them. You take the base in the burette and a measured quantity, about 10 milliliters, you measure it with the help of a pipette. You put it in a flask of the acid. So you take the acid in a pipette here, like you suck it, and you measure 10 ml and put it in a flask. And you take sodium hydroxide in a burette. A burette is a tall graduated rod and a tube which is calibrated, and therefore you can measure how much of the liquid are you using. And then you use an indicator. The indicator is put in. What is the purpose of adding an indicator? Usually for acid-base titrations, we use two indicators, phenolphthalein and methyl orange. Now, the indicator is supposed to be pH sensitive. It will have one color when the pH, it will be neutral at 7. Right? If the solution is acidic, it will have a different color. And if the solution is basic, it will have a different color. So it changes color in acidic and basic mediums. And therefore, that becomes a very good hint for you to act as an indicator. How? If you have 1 mole of sodium hydroxide, you need 1 mole of HCl to neutralize it. You can see it from the stoichiometry of the equation. Now let us say that in 10 milliliters of sodium hydroxide that I took in the flask, I have HCl, and that is 1 molar. Let us assume that solution was 1 molar. And I took 10 ml of it. I would require 10 milliliters of HCl 1 molar to neutralize it. So in the burette, I've taken HCl, which is a standardized solution. I know what its strength is, so I exactly know what its power, how strong is it, what its strength is, what its molarity is, what its normality is. I already know that. I do not know about the sodium hydroxide, but I don't know it. Maybe the examiner knows who prepared the solution. So both of them were 1 molar. So obviously, in order to neutralize 10 milliliters of this solution, you would require 10 milliliters of HCl solution of the same strength. So from the burette, when you start adding it to the flask, the reaction takes place. And you have put phenolphthalein into the, now you take, phenolphthalein is a basic indicator. It turns pink in basic medium. So you have phenolphthalein in the flask and the acid in the flask, and the base is in the burette. So as you keep adding the base keeps reacting with the acid and neutralization occurs. So the medium remains acidic, and if the medium is acidic, the phenolphthalein will be colorless. When you add 10 milliliters of sodium hydroxide, now neutralization has completely occurred. Every molecule of HCl has been HCl has been neutralized by the NaOH. Now when you add 1 extra drop, the medium, the neutral, sodium chloride and water, the solution is absolutely neutral. There is no acid in it. The moment you add 1 drop of the base, the solution turns mildly basic. The moment it turns basic, phenolphthalein, the indicator, turns pink. So you get a very soft onion pink, a very light pink color in your flask. The moment you see that light pink shade on that 1 drop that was added, it means your end point has achieved. That is the volume, that must be the volume of the solution that of the base that you had to use in order to neutralize. So since you know the concentration of the base and you do not know the concentration of the acid, you can, according to the stoichiometry, for 10 ml how many moles would be there, you will calculate that, and an equal number of moles of HCl would be there in that volume, that is the 10 ml that you took. So that is basically the theory of titration, how we do it, why we use indicators. Now what is important in acid-base titrations is that here the indicator is sensitive to the pH. It is sensitive to acidic or basic nature. The same process can be used in case of redox reactions also, because redox reactions are also opposing processes. When a reaction takes place, which is a redox reaction, one of the components will be undergoing reduction, the other will be undergoing oxidation, and there would be a proper stoichiometry or a ratio in which they would take place according to the equation. And if we know the strength of one of them, that is, if we know the strength of the oxidizing agent, you will have to calculate the strength of the reducing agent, which is unknown to you, by the same titrometric method, right? So in the titration of redox reactions, you would also need indicators. And these indicators would be redox indicators. They may or may not be sensitive to acidic or basic medium, but they would be sensitive to the reduction and oxidation, which means that they would have a different color when in the oxidized form, and they would have a different color if the solution mixture, that is the reaction mixture, has excess of reduced form. So it shows different color in oxidized form and reduced form. Therefore, it is known as a redox indicator. Basically, this topic is to talk about these redox indicators and to tell you how they are so helpful. These redox reactions can be used for titration, or how with the help of titration we can estimate the strength of a of one of the components, one of the reactants of a redox reaction. That is the oxidant or the reductant. So let me just read this theoretical part a little. In acid-base titration, we find that the strength of one against the other, we find in acid-base titration, what do? You find out the strength of one against the other using a pH-sensitive indicator. So the strength of one is known, and you find out the strength of the other one by titrating it against the known solution. So you titrate it against the known solution, and for that you use a pH sensitive indicator. And in redox systems, we can find the strength of the oxidant or the reductant using a redox sensitive indicator. So it is nothing but the same process, only the reactions are different. The basic what idea is the same, that you will use an indicator which shows a difference in its color in different mediums. So if you have more of oxidant, it will show a different color. If you have more of reductant in the solution, it will show a different color. So a compound that exhibits different colors in oxidized and reduced forms can be used as a redox indicator. Coming back to acid-base titrations, we use a standard solution. When you do acid-base solutions, we prepare a standard solution. What is a standard solution? A standard solution is a solution whose strength is known to us. Usually we prepare oxalic acid solution, it is easy to measure it and make a very precise solution of oxalic acid. So usually we use oxalic acid as our standard solution, that is the solution whose strength is known to us. Now if we want to titrate it against a base, we can use this standard solution and titrate it against an unknown base, a base of unknown strength, and find out the strength of the base. But if you have a question in which you have an acid whose strength is not known to you, even in that case you might prepare a standard solution of oxalic acid to begin with, and then titrate a base against it, find out the exact strength of the base, and that by doing that you have standardized the base. You get me? Since it is oxalic acid produces a very precise, you can make oxalic acid solution with precise strength or with very accurately. Therefore, we first prepare a standard solution of oxalic acid, and then we, using that, we titrate it against a base, and any base. And then once we have titrated the base against it, we know exactly the strength of the base. So this base is standardized now, and now using this standardized base, we find out the strength of the acid whose strength is unknown to us. So what do you have? You use a standard solution, and if you have to find out about the strength of a base, you might use the same standard solution of oxalic acid. But if you have to find out the strength of an acid, then you will first standardize a base, and using that base you will titrate and find out the strength of the acid. So for acid-base titrations, we use a standard solution of oxalic acid and titrate it against the base. Or we standardize the base and then we titrate it against an acid to find out the strength. And for these we usually use indicators like phenolphthalein and methyl orange. So this was about acid-base titrations, which are a part of your syllabus this year. Now coming to redox titrations, the topic that you are doing this year, but the titrations which you would be doing in grade 12. For redox titrations, we also need a standard solution. So you can prepare a standard solution of either the oxidant or the reductant. And then what would a standard solution be then? A solution whose strength is known to you, whose precise strength is known to you. You're really confident about the strength of that solution. So you use that solution, standard solution of the oxidizing agent or the reducing agent, and we'll titrate it against the other one. For example, if you have the oxidizing agent is a standard solution, you need to find out the reducing agent, that the strength of the reducing agent is unknown to you and you are trying to titrate it against that, or vice versa. Excuse me. Having understood this, let us now talk about the types of indicators. There are different types of indicators, redox indicators. You have self-indicators, you have internal indicators, you have external indicators, you have the potentiometric method, you have starch, which acts as an indicator. And therefore, all of these indicators, they work differently. And therefore, we need to study their titrations separately. In your topic, you are only going to study or understand about these indicators. And in this video, I'm only going to tell you about the first indicator, that is the self-indicator. And in the consecutive videos, we'll be discussing the other indicators. A self-indicator, what is a self? Something that indicates itself. First of all, what is a redox indicator? A redox indicator is a substance which has different color in the oxidant and a different color if the substance is reduced. If you take one substance in the oxidized form and the reduced form and you have an indicator, the indicator would have a different color in its oxidized form when it is present in the oxidized form and a different color in the reduced form. Since it says it is a self-indicator, it indicates itself. It means it's a colored solution, and this colored solution has one color in the oxidized form and another color or no color in the reduced form. So, or vice versa. So in the oxidized and the reduced form, it has different colors and therefore it can indicate itself. It is just like having phenolphthalein, when you had phenolphthalein and you had one drop excess of base, the phenolphthalein turned the base pink and therefore the solution turned pink, and that was your end point. In the case of redox titration, let us say that potassium permanganate usually is the colored substance that is used as a self-indicator or that acts as a self-indicator, and it is an oxidizing agent. It has O4, it has 4 oxygens, therefore it has a lot of oxygen to give, so it is an oxidizing agent, and an oxidizing agent itself gets reduced. So when it is in the oxidized form, that is when it has all the oxygen, it is purple or violet in color or dark pink in color. But when it turns, when it changes, when it reacts and it acts as an oxidizing agent, therefore when it gets reduced, in the reduced form, it is colorless. So what do? We take potassium permanganate in the burette. And when we take potassium permanganate, which is the colored solution in the burette, we take the other substance which is the oxidizing agent, we take the reducing agent. The reducing agent in class 12 that you would be using would be either Mohr salt or it would be oxalic acid. So the reducing agent you will take in the flask, you will use a pipette, you will measure out 10 ml of it, you will put it in a flask and you will titrate it against the potassium permanganate. As long as you keep putting the potassium permanganate into the solution and it is reacting, the potassium permanganate is being used and therefore it is being turned into its reduced form. And since it is being turned into its reduced form, it loses its color, that is the pink color. But when the entire redox reaction takes place, after that, when you add one excess drop of potassium permanganate, it does not have the reducing agent present in the solution to react with. And since it does not have it, it is excess, it comes and it just remains unreacted. At that point, it displays its color because it is a colored solution. It displays its color and that's the end point, and that is the amount of the potassium permanganate that was required to carry out the reaction, to oxidize the oxalic acid or the Mohr salt solution. So let us understand what the self-indicator is once again. When the titrant may be strongly colored, the titrant is the substance, one of the reactants of the titration. When the titrant may be strongly colored, then it may be strongly colored after the end point. It can act as a self-indicator. As long as it is being used, it will turn colorless. But the moment one drop excess is put into it, that last drop is going to display its color. So it will indicate itself. With just one drop of that, it will indicate that, look here, I am here and I have not reacted. So, the end point has come. So for example, potassium permanganate, iodine, which is brown in color, can act as a self-indicator. Cerium sulfate has a pale yellow color, so that can also act as a self-indicator. Usually, potassium permanganate is used to find out the strength of oxalic acid solution or Mohr salt solution for MnO4 negative versus Fe2 positive in Mohr salt, or C2O4 2 negative, which is the oxalate ion. So either with oxalic acid or with Mohr salt, you titrate potassium permanganate and the ion is MnO4 negative. So when this happens, you take potassium permanganate in a burette, you take the oxalic acid or the Mohr salt in the flask, and when you do this, you usually acidify the solution. So you add about a test tube full of sulfuric acid to this. Now the question is, when you add sulfuric acid to it, is it not going to affect the concentration? Is it not going to affect the end point? Because you are increasing the volume of the solution by adding the acid. This reaction is basically based on the stoichiometry. It is based on the number of moles of KMnO4 which will react with a fixed number of moles of the oxalic acid or the Mohr salt according to the stoichiometry of the equation. So that is, for 2 moles of potassium permanganate, 5 moles of oxalic acid is required. So in the ratio of 2:5 they are going to react. So even if you took a fixed amount of the oxalic acid or the iron, let us say oxalic acid because I took oxalic acid here. You took a fixed amount in 10 ml. When you add the sulfuric acid to it, by adding the sulfuric acid, although the volume is increasing of the solution, the 10 ml may increase to 20 ml because you added 10 ml of H2SO4. But that does not affect the total number of molecules of oxalic acid which have to react with the KMnO4. Therefore, it does not affect the end point. Although you may see that the volume has doubled, therefore the concentration should be half. But in this case, that does not matter because the number of molecules that are going to react with the KMnO4 remains the same, and therefore it will not affect the end point. You will still be able to tell that if these were the number of molecules and so much of KMnO4 was used, the original solution should have had so many molecules of oxalic acid, or on the basis of that was the number of moles, or what was the mass of the oxalic acid. You can calculate all of it. You can calculate the strength of the oxalic acid solution. So if you take this equation, for example, this is just to explain how it happens. This is the reduction half. You have MnO4 negative, where manganese has an oxidation state of +7. In the products, you get manganese with 2 positive, Mn2 positive. So this is from +7, manganese is going to +2, which means it is getting reduced. So this is the reduction half, this is the oxidation half, and you have the overall reaction. When you write the overall reaction here, you have, look at the reduction half here, you have 8 H positive ions in the reduction half. These 8 H positive ions actually are because of the acidic medium that you have added in there. And then when you show the reaction, entire reaction, you get 2 MnO4 negative plus 5 H2C2O4 oxalic acid will give, plus 6 hydrogen ions will give you 2 Mn2 positive plus 10 CO2 plus 8 H2. So according to the stoichiometry of the equation, for every 2 moles of potassium permanganate, you will be using up 5 moles of oxalic acid. And that theoretical basis is which makes you understand why we carry out titrations and why we need indicators and what is the role of indicators and how we can find out the strength of an unknown solution. So this was about the first kind of indicator, that was the self indicator. In the next video, I'll be telling you about the internal indicators. With this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel. Please help me spread word about my channel. I'm not able to reach as many students, so please help as many students, as many of your friends or anyone who you feel may benefit from my classes. Please do suggest them to them. And thank you for watching, and bye-bye for now.